right? People kind of, but this is just saying again what we want our programs to look like, right? And don't give me code that doesn't look like this, all right? So what do you have to think? I have some input, A, B, and C, right? Maybe A is a tuple and B is an integer and C is a binary tree, right? And then I have some output that I need to return. I need to return something X and something Y and something Z, right? And every path through this code has to do that. And what's my mission, right? Given A, B, and C, I need to produce X, Y, and Z, right? So, so here, what am I going to do? I'm going to take my A, B, and C and form a different A, B, and C for my friends, right? And A has to be a tuple, and B has to be an integer, and C has to be a binary tree, right? So I do that, and then they need to be valid and smaller. And then I give those sub-instances to my friend. My friend gives me the answer, right? I combine my friend's answer. I trust him. I don't micromanage him, right? Then I combine his answers to get my answer, and I return it, right? And the base case is I have to return a tuple and an integer and a binary tree, right? People kind of follow that? Right? And you'll notice one thing that's here is, right, all the variables, in an iterative algorithm, you keep changing the values of variables, right? But here, each variable only has one value ever. And there's no global variables. There's no, and there's usually not a loop, right? Here, there's not a loop. The only reason you would have a loop is if you have lots of friends, right? And you have to loop. You don't know how many friends you're going to have. No global variables. All right, everybody good with that? So a big part of this course is looking at binary trees. We're going to look at trees, and we're going to balance them, and we're going to do heaps on them. We're going to do lots of things on binary trees. All right? So let's think about them, right? The first, we could ask, what's the definition of a binary tree? And what I would get on tests says, well, every node, it's a tree where every node has two children, right? Does every node have two children? Node 2 doesn't have two children, right? Node 5 doesn't have two children, right? So the definition I would like is a recursive definition. Why? Because it's a recursive structure. And you know my favorite base case is 0. So here, the empty tree is a perfectly good tree, right? Just because it has no nodes, don't discriminate against it. It's a tree, right? So a binary tree is either the empty tree or it's a node that has a left child and a right child. It always has a left child, always has a right child. And those children are binary trees, right? So how does that work? The whole thing is a binary tree, right? Because it's a node 3 with a left child and a right child. Node, left child, right child, right? Why is this a tree? Because it's a node with a left child and a right child, right? Why is this a tree? Because it's a node with a left child and a right child, right? Why is this a tree? Because it's the empty tree, right? Everybody buy that? All right. So now we're going to be doing recursion to solve some problem on this tree. And our goal, this is just what we have kind of written over here. I'm going to have two friends, right? Each of them, I don't know the balance here, but more on average, their input size will be n over 2. And I personally only want to do a constant amount of work. All right? So what can I do in a constant amount of work? I can look at the root node. I can pass constant information to my friends. I can get a constant information from my friends. I can combine their information to get my information, right? That's what I can do in a constant amount of time. And so you don't want to do more than that, all right? Right, suppose I want to know the number of nodes in the tree, right? Claims it's 12, all right? How do I do that? Well, I will have a recurse for each of my subtrees, right? And what do my subtrees do? They return the number, they solve the same problem, right? So they tell me the number of nodes. And then how many nodes do I have? I have the sum of my friend's answer plus 1. Right, everybody see that? Constant time per node. Right, there's be one stack frame per node. Right, I don't have time to look at the subtrees, right? You have to trust your friends. Right, I think about it is there's a wall here, and you can't look at your subtrees. All you can do is get a constant information from your friends, right? Does that make sense? Right, so the precondition says I've been given a tree and I need to return some information. I think this is more than we need. Let's get. Right, this is just saying sometimes you might want to give your friends extra information, right? You might want to tell this friend, hey, you're the left tree. You tell this friend you're the right tree. They might want to know that, right? Or maybe you get extra information from your friend, right? From your friend, you're told not just the number of nodes, but you want to learn the height of the tree as well, right? So you can change the pre and post condition to allow you to have more communication, all right? That's just those. All right, so what's our base case, right? Here we could say there's one node, right? Are we done? What should our base case be? Well, how do you solve this problem, right? So one thing I don't like is I've seen in books where they have all these, their base case is one node. And then they have all these cases. If I have a left child and not a right child, if I have a right child and not a left child, if I have both children, if I have no children, right? They have all these cases. Do I like that? No, right? So let's not do that. Let's just say, let's have our base case be that we have no nodes. And how many nodes are there? 0, right? And then, right, does 7 got the right answer? Yeah, it's going to be 0 plus 0 plus 1 is the answer, right? Everybody see that? Yeah? So the code will say, if I'm the empty tree, then the answer is 0, right? So what does 2 do? Oh, what does 7 do? 7 says 0 plus 0 plus 1 equals 1, right? What does 2 say? It says 0 plus 1 is 2, right? Right? So don't have so here's the code. I'm given a tree. If my tree is the empty tree, return 0. Otherwise, return the number on the left plus the number on the right plus 1. Right? And of course, if you're doing this in Java, you gotta turn it into Java, right? In fact, one more sentence about that. In Java, right, we have tree is pointing at some object which is a tree, and it has a root which is pointing at the root of the tree, right? And when I'm passing tree here, I don't want to pass this because then I have to work hard to get my children, right? What I want to pass is this value. So I can easily get, I mean, it's the pointer to this, right? So you can easily get your children. But we can talk about that again later. All right. So now you want to check. You wrote the code, and you want to check if your code works. So you try the various cases. The first case is when you have a big left and a right. And does it work then? Yeah, it works then because that's the code we wrote it for, right? Does it work in the base case? Yes, because we wrote it for that. So now we check the others. Does it work here? Yeah, it does, right? Does the same code work here? Yeah, it does, right? Everybody see that? So it's working in all of these cases, right? And then what's the running time? Well, each stack frame does a constant amount of work, right? So if this is our tree, then what's our tree of stack frames, right? It mirrors it, except you have all these base cases hanging off. But the number of nodes doesn't more than double, right? And so the number of stack frames is order n, and each does constant work, right? So the total work is order n, which is kind of what we did here. Yeah? I think the question is indicating that you're thinking iteratively instead of recursively. All right? So it's not like I do something iteratively until I stop, right? This is the code, right? Well, you can kind of say, I have an input, and I give my input smaller to my friend who gives it to his friend to give it to his friend. When does that process stop? It stops when you hit a base case, when you hit a leaf, right? But I don't want you to think that way. I want you to think, I call my left friend, I call my right friend, I put their answers together, I go home, right? So here, what we were doing over here with recurrence relations doesn't quite work because we don't know how big our left and right will be balanced, right? Here, I'm assuming they're balanced, and you get the answer we wanted, right? But here we can solve it this way if we wanted to, right? The time for all the trees is the time on the left plus the time on the right plus some constant c, right? So we guess that if every guy is doing work c, then the total will be c times n. So you plug in your guess, and then you factor out the c, and you see that this is a true statement. right? The number of nodes in the tree is the number on the left plus the number on the right, right? So that's just, all right, everybody good with that? So now, let's say we have many children, right? So what do? We ask each of our children how many nodes there are, and we add them up and we add one for ourselves, right? Does that make sense? And so here's some code, and it has a loop, right? Because we don't know how many children we have, right? So if it's an empty tree, I give 0. Otherwise, I'm going to start in being a counter of how many I have. I loop through all my children. For each child, I recursively call and count the number of nodes in my child, right? And add it up. And then I return one more, right? Can people follow this code? Yeah, no, maybe so. Any questions about the code? Everybody dying? Everybody enthusiastic? Anybody have a question? Anybody want me to do it again? Right? Here, what are we doing here? I have a tree. Somehow my tree knows how many children I have, right? So I'm indexing my children from 1 to the number of children. Why? Because I'm not a Java person. I don't index from 0, right? So then I go through all my children. And here I'm working on, this is going to be my ith child, right? Tree's ith child. And here I'm recursing. Here's a program that gives you give it a tree and it tells you how many nodes are in the tree, right? So I give it this subtree, right? And what does it say? It says how many nodes are in that tree, right? I do that for all my children, right? N is going to keep a running sum of how many children I've seen so far, right? So now N is the sum of the children, right? And then I add 1. What's the plus 1 for? The root, me, right? Everybody get that? All right. So does it work? Yeah, there's the generic case. If I have one child, yeah, it just has one friend. If I have no children, right? How many times does it go around the loop? 0, right? You look back at the code here, right? I have 0 children. It's going to do this loop 0 times, right? And return 1, right? All right, so here's some shorter code. And so it doesn't have a base case, right? We say, how can you have code without a base case? Now, the precondition is telling you that you can't have the empty tree, right? Empty trees just don't exist, right? So how is this, what is it doing? I mean, it said for a general tree, it still is the same. We start at 1 and we count for all our children, right? So how are we going to stop? Oh, let's go back to this thing, right? Program works for this case, right? We have one child that works. This case doesn't happen. What about this case, when you have a leaf with no children? What happens? That's kind of becomes the base case, right? Because you have no children, it doesn't recurse, and it works, right? So in this case, it's a little harder because there's a loop. And so I'm not doing a constant amount of work. The amount of work I do is kind of the number of children I have, right? So I've struggled explaining this to students over the years, and I think the best way to think about it is, let's talk about how many edges are in the tree, right? So in the code, how much work I do, I do work for each edge, right? Each node does work for each edge, right? Because it's looping over the children. So the amount of work a node does is the number of edges. And so in some ways, the total work is not the number of nodes, it's the number of edges. All right? But now we've done that. How many edges are there? Right? So, and note that we never counted the same edge more than once, right? I mean, it's just one work per edge. But now you look at every node. Instead of saying this node, who are the edges coming out? That's confusing. Let's talk about who are the edges coming in, right? Each node only has one parent. So that tells me that the number of nodes is in fact, the number of edges is in fact one less than the number of nodes, right? Because the root doesn't have an edge coming in, right? So that's just kind of what all that says, right? And what do you need to remember here? It's still linear time, right? How are we doing for time? Are we running out? 5 minutes. All right. This is what I was drawing over the board here, right? When I first taught this course, Frank, who's now an assistant dean, was in the office next to me, and I went next to him and I said, "Can't recursively do this, right? Because if I'm given a tree that looks like this, to get my subtrees, it's hard, right? I have to form new objects called trees and put these subtrees in them, right? And we don't want to do that. So instead, when I pass the name tree, I'm really passing the pointer to this. And then to my friends, I call the pointer to this and the pointer to this, right? Right? So here, right, you're not passing it a linked binary tree, right? You're passing it, right? Because the linked binary tree, you want to pass it whatever this value is, right? Right? We don't want to build. So instead, we pass tree, which is of type node, right? Pointer to node. People kind of follow that? And so then, if we have the tree, there's ways of getting the left tree, right? If tree is pointing to this, then tree dot left is pointing to this, and tree dot right is pointing to this, right? And I think we should stop, because I think that's good. Everybody more than that's happy, right? Then we'll do more examples later. Have a great 10 days. I'll see you in 10 days. Any questions about anything? Yeah? It's not in the class. We should figure out where it is. Do you know where it is? What? In the right, in Lausanne. Williams Center. Oh, I'm not sure I've ever been to the. Yeah. Cars from chemistry. All right. I know where chemistry is. We used to be in the chemistry building. Have you ever gone to that's across from the chemistry building? Yeah, in the basement there. All right, good. All right, well, we'll see you all there.
Professor.
Anybody have any challenges in life? You good?
Hello, Professor.
Me. You can write me email over the holiday. Try to relax some. Bye.
Hello. Damn. No audio.